Hello, welcome to my channel. Today we are going to solve a common collector amplifier circuit and simulate the circuit on a simulation software to validate the results. So for in a common collector amplifier circuit, the configuration is that we provide the input at the base and collect the output at the emitter side. There are certain characteristics of the common collector amplifier. It's that it has very high input impedance and very low output impedance, and its voltage gain is close to unity. That means it's approximately 1, 0.9 or 0.8. For the biasing technique, we used voltage divider biasing technique. In other circuits you might see the two emitter supply biasing. Both of them works. So this common collector amplifier is mostly used in cases where the input driver has very high impedance and the load has very low impedance. So when we connect those two things, there is a impedance mismatch which causes a drop in signal. So to prevent this, we connect a common collector in the middle, and the high impedance of the driver matches the high input impedance of the amplifier, of the common collector amplifier, and the low output impedance matches with the low impedance of the load. As a result, that signal loss is prevented. For this video, I'm not going to show any derivation, but in this solving tutorial we are going to focus on three parameters, that is the input impedance, as I said, the input impedance, output impedance, and the voltage gain. I'm going to write out the equations for all the three parameters. So at first we're going to focus on the voltage gain. Voltage gain AV is equals to the output divided by the input. The output is the emitter, that means VA, divided by the input, that is VB, that is the base voltage. For the emitter side, we have IE into RE. RE is the parallel of RE capital and REL. That means the load resistance and the emitter resistance. On the denominator, this is the base voltage VB. Therefore we can consider this region, this entire region, that is IE. Then we have the dynamic resistance, the AC resistance of the base emitter junction, plus the emitter resistance. You can cancel it out. RE divided by RE prime plus RE. The reason we say that the gain is almost equals to 1 is because RE dash is very small compared to RE. The RE is in kilo ohms range and RE prime is in ohms range. Therefore we can say that 1 is approximately equals to 1. Then we focus on the input impedance. Zn is equals to the impedance is divided into three regions, R1, R2, and the Zn base, that is the input impedance of the base. So R1 parallel to R2 parallel to Zn base. The Zn base is equals to the impedance affected by this region, that means beta multiplied by Re prime plus Re. Therefore Zn is equals to R1 R2 beta Re prime plus Re. Re will be provided, we can calculate it from these two. R1 will be provided, R2 will be provided, beta will be provided 100. Re prime we have to calculate. Then finally for the output impedance is equals to, output impedance is from this region, it gets divided, the impedance is getting divided into two. We have Re, then on this region the AC, the dynamic resistance, then we have R1, R2, and the generator resistance, the internal resistance. Therefore we can say that Re parallel to Re prime plus on this region, therefore we will divide by beta. Beta will be on the denominator, plus R1 primary R2 Rg divided by beta. So Re will be provided. We can Re is provided, R1 is provided, R2 is provided, Rg is provided. Same with beta, we have to find Re prime. Therefore, to start our mathematical problem, we have all the values. At first, we are going to find Re prime, which is the dynamic resistance. So Re prime is equals to 26 millivolt divided by IC. Before finding IC, I want to say is that when we start learning about BJT based amplifiers, we stick to certain conditions. That is, IC is almost equal to IE. That is, IC almost equal to IE, and IB is equals to IC by beta. These are fixed conditions that we stick to. Therefore, I can say that since IC is almost equal to IE, I can find IE. Therefore, IE is equals to VE divided by RE. I have RE, which is 10K. I need to find VE. To find VE, I need to calculate VE. To calculate VE, we can start from this position, that is the divider voltage. The divider voltage, we can calculate divider voltage using the voltage divider rule. For example, VE is equals to VD minus the divider voltage is that VD is equals to 20K, that means this 20K divided by 20K plus 20K, divided by 20K plus 20K into 20 volts. That means we get half 10 volts. VD is equals to 10 volts. So in this region, the voltage is 10 volts, 10 volt. Then there is a further voltage drop, which is 0.7. That is the base emitter voltage drop. So 10 minus voltage drop of 0.7, 10 minus 0.7 will give us 9.3 in this region. Therefore, VD, which is 10 minus 0.7, will give us 9.3 volts. Therefore, our VE is equals to 9.3 volts. I can agree that IE is equals to VE divided by RE. VE is 9.3 volts. RE is 10 kilo ohm. IE is equals to 930 microamperes. Therefore, IC is also equal to 930 microamperes. So now we can find, therefore, Re prime is equals to 26 millivolt by 930, which is 28 ohms. 28 ohms. By finding this parameter, now we can approach for Z in and Z out and the voltage gain. Therefore, Z in is equals to 20K, okay, parallel with another 20K, parallel with the beta is 100, 28 plus 10K RE, 10K parallel with 500, 10K parallel with 500. In total we get 8.35 kilo ohms for the input impedance. For the output impedance, Z out is equals to 10K RE parallel with 28 plus 20K 20k parallel with the RG is 1 kilo ohm. Internal resistance of the source of the driver resistance is 1 kilo ohm. So 1 kilo ohm divided by beta, which is 100. Z out we get as 36.95 ohms. We found the input impedance, we found the output impedance. Now it's the most important parameter, which is the voltage gain. V is equals to 10 kilo ohm 10 kilo ohm parallel with 500 kilo ohm parallel with 500 divided by 28 plus 10 kilo ohm parallel with 500, because the formula is that RE, which is the parallel of RE RL. We did this, we calculated this. Again, this is the same as this. So our gain is 0.944. Now you might think this is the actual gain, but this is not the actual gain, because in this equation we neglected the 1 kilo ohm at the source side. We neglected the 1 kilo ohm at the source side. Because of this 1 kilo ohm, our gain will be reduced. So we need to find, at this region, we need to find the divider gain. Therefore, divider gain is equals to AD is equals to the input impedance 835 kilo ohms divided by 835 kilo ohms plus 1 kilo ohm. That is, we get 0.893 as our gain. So the total system gain, which is the actual gain, is 0.944 multiplied by 0.893, which is 0.843. So our output voltage will be is equals to 0.843 multiplied by 100 millivolt is equals to 84.3 millivolt. This will be our output voltage, 84.3 millivolt. We go to AC analysis and select node voltage so that we can measure the node voltage at the load side. We get approximately equal to 84.74 millivolts, which is close to our calculated value. Our calculated value was 84.3 millivolts, so our simulated value is a little bit higher than our calculated value. So then we check the divider voltage. Our calculated divider voltage was 10 volts. The simulated value shows 9.94 volts, which is close enough. Then our emitter voltage was calculated value was 9.3 volts. The simulated value is 9.29 volts. Then to check the collector current or the emitter current, we go to DC analysis and click on R3, the resistor. We can see that our calculated value was 930 microampere. Our simulated value is 929 microampere. We click on transient analysis to check the voltage versus time graph, in which will contain the input and the output curve. If you check the label, VG1 is the input curve and VF1 is the output curve. So that's it for today's video. Thank you for watching.